Hello, everybody, and welcome back to the non-existing series Science is either consistent or inconsistent. Today we are going to discuss an example from nuclear physics, and before getting into that, let me tell you some introductory notions to that example. First, and the most important, the nucleus of an atom. The nucleus of an atom is the smallest region in which 99.9% of the total mass of the atom is located. The nucleus consists in protons and neutrons that are bound together. The protons are responsible for the positive charge of the atom, and the behavior of the nucleus is explained by appealing to two different forces, the strong nuclear force and the weak nuclear force. First, the strong nuclear force is what binds nucleons, protons and neutrons, into an atomic nuclei, while the weak force is responsible for the decay of neutrons to protons. Any atomic nucleus, for any chemical element, will exhibit binding between protons and neutrons as well as decay of neutrons and protons. The binding energy of a nucleus is what in large part determines the stability of the nucleus. Ideally, binding energies are necessary for understanding and determining under which conditions a nucleon can change to another, from neutron to proton, for instance, or escape from the nucleus. Considering that binding energies are necessary for predicting and describing different aspects of the nuclear structure, for instance correlations present in nuclear ground state, physicists have tried to come up with homogeneous theoretical frameworks to calculate this type of energy. However, as today, there are 31 different successful and internally consistent nuclear models that offer some kind of insight into the nucleus of the atom. There is a whole theory that can explain what the atomic nucleus is, but at the time of predicting and measuring, we have to use some of these 31 different and successful models of the atomic behavior. These models are often classified into the three main groups: microscopic models, which focused on nucleon-to-nucleon reactions; collective models, which focused on bulk properties of the nucleus as a whole; and mixed models, which are somewhere in between the two previous ones. The diversity of the models is obviously not problematic, especially if each model has its particular successes, and together they are sometimes taken as complementary, insofar as each contributes to an overall explanation of the experimental data. So, instead of having a problem, we have way too many, or at least 31 different tools to operate on the same entity, the atomic nucleus. So we are very rich in that respect. Now, one of these models, the liquid drop model, this is one of the oldest and the most successful models that we have in nuclear physics. It was formulated more than 80 years or 90 years ago under the assumption that the nucleus of an atom exhibits classical behavior. Protons and neutrons strongly interact with an internal repulsive force proportional to the number of nucleons. The main idea is that the nuclei will separate as a drop will do if pressing with enough force against it. So that's the main idea behind the liquid drop model. At the very beginning, this model could predict and describe a series of nuclear properties, and especially it does so by appealing to very little different calculus. So the operations and the predictions are quite straightforward, and that is the reason why the liquid drop model is so successful. However, despite its successes, this model fails to describe the way in which nucleus are often displayed distinctive energies in different levels, forming shells and subshells, what is often called the so-called shell effects. It also fails to give account for the ground state properties of a nuclei, among other things. But that is fine, because we have other three models that can help us with that. So we might have a problem if the model is expected to give us successful results in a particular domain and it doesn't do so. And we don't have any other alternative for explaining why the model is not successful in an expected domain or a desired domain. And so this hadn't happened before. But suddenly, during the last century, a new phenomenon was discovered. This phenomenon is called the magic numbers effect. So let me tell you a bit about it. Experimentation has shown that some nuclei are bound more tightly together than predicted by the liquid drop model. Depending on the number of nucleons that this nuclei possesses. To explain this phenomenon, scientists have referred to it as the magic numbers. The phenomenon can be detected in the nuclei of atoms at least that include helium, oxygen, calcium, nickel, and lead. And what happens is that the model cannot help us predict in a successful way how much energy we need to separate this nuclei, to get fission. And so, but it is very successful in the other elements. What we have now, it's a problem of not being able to explain why the model is successful with some elements and not successful with these ones. Additional to that, and maybe more importantly, we are unable to use our very reliable model to predict the binding energies for helium, oxygen, calcium, nickel, and lead at least. But the partial failure of the liquid drop model does not mean that scientists are left empty-handed, and this is the most important thing. When dealing with the phenomenon such as the magic numbers, physicists often relied on the other models, one of the most important being the shell model. This nuclear model is a bit younger, so it was formulated more than maybe 70 years ago and aims at describing and predicting, among other things, nuclear shell effects of the nuclei, and also can account for the binding energies of these particular elements, the ones related to the magic numbers. Accordingly to the shell model, the nucleus exhibits itself a quantum mechanical type of behavior. For this model, nucleons are assumed to be point particles free to orbit within the nucleus due to the net attractive force that acts between them and produces the net potential while drawing all the nucleons toward the center rather than toward other nucleons. One of the most important features of the shell model is that it accounts for the magic numbers phenomenon, among other important experimental data. What is happening here is that we have two models, of which one is assuming that the behavior of the atomic nucleus is classical, and the other one is assuming that the behavior of the atomic nucleus is quantum mechanical type of behavior. So far, this shouldn't be problematic. Nonetheless, while the shell model can help us to deal with the magic numbers phenomenon, it cannot get us till the end of the prediction of fission. The only thing that the shell model can do is help us to generate a prediction of how much energy we need to break the atomic nuclei, which is called binding energy. So the first thing when we are trying to predict fission or measure fission is that we have to calculate binding energies for the atomic nuclei that we are working with. Once we have already calculated that, then we can move to predict fission. This is a prerequisite of us measuring and predicting when fission will occur. If we were dealing with the magic numbers elements and we were only having the liquid drop model, we wouldn't be able to do that because the first step is not out at our reach because of the type of phenomena that we are dealing with. But if we use the shell model, we can neither do that. We can only get to the binding energy measurement, and then we cannot move straight ahead to fission. So what physicists have been doing is combining both elements. So they use first the shell model in order to calculate the binding energy of the element that they are working with. Then they change the model and move to the liquid drop model. But what is happening here is that the assumption is that first, that particular nucleus works as a quantum mechanical entity, and suddenly it changed to become a very classical type of thing, a liquid. That's it. It seems that we have to explain how this practice is rational. So either it is inconsistent or consistent, but more importantly, how can they assume that the same atomic nucleus for the same particular phenomenon, which is fission, behaves at different moments of the calculation, but not of the phenomenon, as different? And that is a reliable tool for getting good predictions. Thank you for bearing with us, and see you in the next edition of this non-existing series. Bye!